Hello, everybody. This is Professor Jing. This week, we're going to talk about survival analysis. We will dive into this fascinating statistical method that allows us to get meaningful insight from time to event data. So, what is a survival analysis? Survival analysis is a powerful tool used in various fields, from medical research and engineering to business and social sciences. It helps us to understand the time until a specific event of interest occurs, such as patient survival, equipment failure, and customer churn. The primary goal of this week's lecture is to introduce you two fundamental concepts in survival analysis. First, the Kaplan-Meier estimate to the survival function, and second, the proportional hazard model. The Kaplan-Meier estimate is a non-parametric estimate that enables us to calculate the probability of survival at the different time points, even when we have incomplete or censored data. I will walk you a step-by-step calculation and see how to interpret the results. Next, we will explore the proportional hazard model, a semi-parametric model widely used in the survival analysis. This model helps us examine the effect of covariance on the hazard function, providing valuable insight into the relationship between these variables and the event of interest. So at this time, you may ask, what exactly is survival analysis? Well, in short terms, it is a statistical tool used to analyze time-to-event data. The core idea here is to study the time it takes for a particular event of interest occur. Now let's talk about the event of interest. This event can be anything from the occurrence of disease, failure of mechanical system, or even customer churn in a business. The key is to understand when these events are likely to happen and what factors influence the timing. However, real-life data is not always straightforward. In survival analysis, we often encounter what's called censoring. This happens when we don't have complete information on some individuals in our study. There are two types of censoring we commonly encounter. The first type is called right censoring. It occurs when the event hasn't occurred for some participants during the study period. We only know that it hasn't happened yet. The second type is called left censoring. Here, some individuals already experienced the event before the study began. We only know the time interval between the event and the study starts. You might wonder why this is important. Well, understanding survival analysis and handling censoring is critical and crucial for making the meaningful conclusion from our data. By analyzing time-to-event relationships, we can identify risk factors, compare treatment outcome, and make informed decisions in the wide range of fields. Let's consider clinical trials as an example. Imagine we're studying the survival time of patients with certain disease. Now, some patients might still be alive at the end of our study. Their data is right censored because we don't know when they will experience the event, which in this case is death due to the disease. Survival analysis help us estimate the probability of these events occurring at different time points. The Kaplan-Meier estimate is a non-parametric estimator used to calculate the survival function from the time-to-event data. It is particularly valuable when we have censored data, which means that some individuals in our studies have not experienced the event of interest within the observation period. So how does the Kaplan-Meier estimate exactly work? Let me show you the step in the next slide. First, we need to order our data in ascending orders based on the time to event variable. Then we need to initialize the survival probability to 1 and the number of risk to the total number of subjectives. Next, we iterate through the data event by event. For each event time, we calculate the survival probability at that time. It is done as follows. We take the previous survival probability and multiply by the proportion of surviving subject at that time. This step-by-step calculation gives us the estimated survival probability at the various time points. The Kaplan-Meier estimate is well suited for scenarios with sensor data because it accounts for subjects who are still at the risk of experiencing the event but have not done within our study period. This makes it a powerful tool for analyzing real-world data, where not all the events occurs during the course of the study. Let's go through an example to understand the process better. Imagine we have data for a group of individuals and their event time are 10, 15, 20, 25, and 35 units of time. Some experiencing the event denoted as 1, while others were censored, denoted as 0. We start by ordering the data and setting the initial survival probability to 1. As we iterate through the data, we calculate the survival probability at each event time, considering the number of surviving individuals at that specific time point. The resulting Kaplan-Meier estimate produces survival probability at different time points. As we plot this probability, we get the Kaplan-Meier survival curve. So if you plot the survival probability, you will get what is called as Kaplan-Meier estimate curve. This curve is shown on the left-hand side, and it is a fundamental visualization tool in survival analysis. It displays the estimated survival probability over time, revealing the likelihood of individual surviving up to each time point during the study. It helps us understand how survival chances change over time and provide us crucial insight for decision making in various fields. Let's talk about proportional hazard model. So the proportional hazard model is a semi-parametric model used extensively in survival analysis. It enables us to examine how different factors influence the risk of experiencing the event of interest over time. First, let's discuss the key assumption of this model. The first assumption is the proportional hazard assumption. This is the fundamental assumption of the model. It states that the hazard rate between any two individuals remains constant over time. In other words, the effect of a covariance on the hazard is constant throughout the observation period. The second assumption is independence assumption. It assumes that the occurrence of event for one individual does not affect the occurrence of the event of the other individuals. Each individual's event time is considered independent of the other. Now let's focus on the Cox proportional hazard model, which is the most commonly used version of this model. One of the key advantages is flexibility. The Cox model does not assume any specific distribution for the base hazard, allowing it to be more flexible and applicable to a wide range of datasets. In this class, I don't expect you to do calculation by hand, but I want you to have some idea about what the model does and why do we want to use it. Now let's talk about how we interpret the results of proportional hazard model. So the main parameter of the interest in this model is the hazard ratio, or HR. The hazard ratio represents how the hazard rate change for a 1 unit change in the covariance while keeping the other covariance constant. If the hazard rate is greater than 1, it indicates an increased hazard. This means that covariance has a positive effect on the event, making it more likely to happen. Conversely, if the hazard rate is less than 1, it suggests that there is a decreased hazard. This means that the covariance has a negative effect on the event, reducing the likelihood of its occurrence. Finally, if the hazard ratio is equal to 1, it indicates that there's no effect on the hazard rate. In this case, the covariance has no impact on the event of interest. That's all I have for this week. I hope this lecture will give you some idea about survival analysis. And if you have any questions, please feel free to contact me. Thank you.